Okay, lab 4. So the purpose of this lab was to understand Faraday's law, model a magnet-tube interaction, and compare predictions of this interaction with observed data. The fundamental principles include Faraday's law, Lenz's law, and the magnetic field slash magnetic flux. So Faraday's law states that when a magnetic flux changes, there is an electromotive force generated across a coil. Lenz's law states that the current flows in the opposite direction of which it is produced, or the force from the current flows in the opposite direction. So there's a magnetic field created in that direction, the opposite one. And my results were that I had 0.31, 0.46, 0.45, 0.45, and zero point 0.6 seconds for the time it takes for it to come shooting out of the tube, which is 0.454 seconds for an average. So again, going over the models, Faraday's law, the change in flux is moving downwards and it induces a current. And for Lenz's law, the induced current must be pointing upwards because it's the opposite of the force kind of thing. And the current flows upwards due to the right-hand rule as well. And then there is a magnetic force from the barb magnet, and this can be calculated using Biot-Savart's law. So the experiment was to create a tube of aluminum foil and drop a bar magnet through it, then time how long it takes the magnet to fall through the tube, and average this in 5 trials. And from the forces, the bar magnet is supposed to float, so it will take longer for it to reach the bottom of the tube. These are my initial conditions: 0 for the velocity, 0 for the start position. So it's 10 inches long and 0.5 inches thick and 1.5 inches wide for the opening. System versus surrounding. Surrounding is the universe and the tube, and the system is the bar magnet, not the aluminum foil. I need to change that. Slay. Physical errors. Tube was a perfect cylinder. Was not a perfect cylinder, so there was a lot of surface areal bumps and things like that. So it's shouldn't be modeled as a perfect cylinder, even though it is in the code. It didn't drop in the exact same height each time. That was not something that I had constant. So that could also affect the time. There also might have been friction from the irregularity in the tube inside of it, because it could have been hitting the walls of the tube. That could be making it take longer. Results again. So this is the code, and just kind of going, through the code using Biot-Savart's law to get the magnetic field of the magnet, and then calculating the flux, and then calculating the force of gravity and the magnetic force of the flux and how that's pointing upwards and all that jazz to have a net magnetic force going down that's smaller than gravity. I hope I explained that well. And then this is my graph. And then also something weird about my graph is I feel this should be more static, but I had a lot of oscillations, which is odd, and I don't really know why it did that. I guess it's just something weird to do with the force. It's going up and down and whatnot. But yeah, so that is the simulation, and this is the position vector. It's going down, and this is the velocity. So we have some stagnant, some constant velocity, yes, that is not changing. Anyways, so similarities and differences in the code. So 0.454 seconds measured in real life and 0.7 seconds for the code. This could be from the fact that the expected magnetic force was bigger in real life, or that the upward Faraday's force was a little stronger than that of gravity, which would make it take longer. There's also air resistance and possibilities that the aluminum foil was too thin to really have strong effects for errors. Those are the errors. Also in the code, the mu from the previous labs could have been wrong, so the prediction could have been wrong. And why a non-ferrous tube? Iron has ferrous magnetic forces that would interfere with Faraday's law. So what if / conclusion? So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So due to Ohm's law, it would increase the induced current, making it take longer for the magnet to leave the tube, because we have Faraday's law saying that that current is going to create a force, and then Lenz's law saying that force is going to be the opposite direction that it's falling, so that would be upwards, bigger upwards force, smaller net force going down. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So this could reduce the induced current and magnetic force because it would have less rings, and make the bar magnet fall way faster because the model, of course, would have less rings, not wings. LMAO. Okay, thank you so much. I'm going to end it now. Bye.